L'Hopital's rule is one of the cornerstones of Calc 1. It is profoundly useful and really pretty fun to use. Let's motivate this a bit with an example first, and then we'll jump into the theorem itself. Here's one that we might have seen when we studied limits several sections back. We have the limit as x goes to 2 of x squared minus 4 over x squared plus 2x minus 8. And what we did, so we'll do it the old way, and then I'll show you a new way of doing it with L'Hopital's rule. So here's the old way. Well, we went ahead and tried to evaluate the limit, so we put in 2, and we get 0 up top. Putting in 2 in the bottom, gives us 0 again. Well, 0 over 0 is an indeterminate form. And what an indeterminate form means is that this basically tells us absolutely nothing about what this limit could be. This limit could evaluate to anything, but when we try to evaluate it in its current form, we get 0 over 0, which essentially tells us nothing other than the fact that we have problems, we have to do more work. So what we did before is we went in and factored and then tried again. So let's do that. Okay, we still have our limit as x goes to 2, but now I'm going to factor both the numerator and the denominator. Up top we get x plus 2, x minus 2, all over. Down below, let's see, how does that factor? I'm thinking x plus 4, x minus 2. And there we get our cancellation. We now try the limit again, and indeed we get 4/6, which simplifies to 2/3. Okay, that's the old way. It does the trick because it gives us our limit, but it's a little bit tedious because we have to factor, and it's probably pretty limited here because there are going to be a lot of expressions that don't factor. So once we get some variety, this old method isn't going to work. So let's try it another way. What if we just tried taking the derivative of the top and the derivative of the bottom, and then evaluating the limit that way? So instead of our limit as written, I'm going to write this as the limit as x goes to 2. That stays the same. And now derivative of the top is 2x. Derivative of the bottom is 2x plus 2. Evaluating that immediately gives 4/6, which we already know, of course, is 2/3. Well, that's faster and it requires far less brain power, and it's what's known as L'Hopital's rule. Let's take a look at L'Hopital's rule in more detail. Okay, so here we go. L'Hopital's rule. Suppose that f and g are differentiable on an open interval I containing a, with g prime of x not equal to 0 on I whenever x does not equal a. Okay, that's just getting the preliminaries out of the way. Here we go with the rule itself. If the limit as x goes to a of f of x over g of x equals 0 over 0 or infinity over infinity, then the limit as x goes to a of f of x over g of x equals a limit as x goes to a of f prime of x over g prime of x. Okay, the rule also applies if x goes to a is replaced with x goes to plus or minus infinity, x goes to a from the right, or x goes to a from the left. So really a very broad rule here. It can be applied in a lot of different applications, as we will see. Some things to note here. First off, this is not the quotient rule. It's actually much easier than the quotient rule because we're simply taking the derivative of the top and the derivative of the bottom. No low d high minus high d low, none of that. The other thing is that you must check that the original limit equals 0 over 0 or infinity over infinity. Right, the conclusion of the theorem here doesn't hold unless you show that the hypothesis at the beginning first holds. So I've seen countless instances where people jump straight into the conclusion of the theorem without bothering to verify the 0 over 0 or infinity over infinity part, which gives you an erroneous conclusion. So it's not just there for looks, it's actually a really important part of this theorem. An interesting fact of this is L'Hopital didn't actually come up with L'Hopital's rule. It was actually Bernoulli, and this was in the late 1600s in France, and L'Hopital was publishing a textbook and had an agreement with Bernoulli that he could take credit for anything that was published in the textbook. And so this is Bernoulli's result, but it was published in L'Hopital's textbook, thus it became known as L'Hopital's rule. Okay, enough with the theory. Let's try this out on some examples. Okay, so it says use L'Hopital's rule to evaluate, and then for part A we have limit as x goes to 0 of sine x over x. Do you remember this limit from a previous section? We essentially memorized it because it was such an important result for all of our trig derivatives and everything else. But now we don't have to remember what it is. It doesn't matter because we can quickly use L'Hopital's rule. First thing we always do with any limit is try to evaluate it flat out. Don't launch into these derivatives until you've tried the limit without L'Hopital's rule. Let's see, we have the limit as x goes to 0 of sine of 0, which is 0 over 0 as x goes to 0. So that is indeterminate, but that's a good thing for us because it has to be indeterminate to use the theorem. So then we say, okay, this equals, and usually you put a little h saying that we're using the theorem here. So this equals by L'Hopital's rule. The limit as x goes to 0, that still stays. We're still doing a limit. Derivative of the top, cos x. Derivative of the bottom, 1. Well, cos of 0 is 1, so this is 1 over 1 equals 1. Maybe you remember that that's what this limit comes to. Maybe you didn't, but now you don't have to remember anymore. You can let that go out of your memory for good because now we have L'Hopital's rule and it's very fast to get it again. Let's try part B. We have the limit as x goes to e of natural log x minus 1 over x minus e. If we straight plug in e for x, we get natural log of e minus 1 over e minus e. We'll recall that natural log of e is 1, so this is indeed 0 over 0. Well, that's bad news because it's an indeterminate form, but it's good news for us because it's exactly the form we need for L'Hopital's rule, and I can't stress enough how important it is to check that before proceeding with the rule. Alright, now we hit it with the derivative of the top and the derivative of the bottom, so this equals by L'Hopital's rule. The limit, we're still taking the limit as x goes to e. Okay, derivative of natural log x is 1 over x. Minus 1 goes away. Derivative of x is 1. So this evaluates to 1 over e. Okay, for part C, we have the limit as x goes to infinity of e to the 3x over 3e to the 3x plus 5. Well, the first thing to do here is to evaluate this limit with just plugging in. That would give us infinity up top and infinity on the bottom. That is what we need. It is indeterminate of the correct form to proceed with L'Hopital's rule. So let's do it. We say equals by L'Hopital's rule. We hit it with the derivative of the top, derivative of the bottom, not using the quotient rule here. Derivative up top, that's 3e to the 3x. That's just the chain rule applied to e to the 3x. Over down below, we have 9e to the 3x. And then the plus 5 drops off when we take that derivative. The e to the 3x is now cancel, and we have 3/9, which of course is 1/3. So it's very quick to use, and I would argue a heck of a lot more fun than the quotient rule, though these computations do become a little more involved when you have a different kind of indeterminate form, such as 0 times infinity, or maybe something like infinity minus infinity, or maybe 1 to the infinity, right? There's several other types of indeterminate forms that we'll look at that will need to give a little bit more thought before proceeding with L'Hopital's rule.